back to 0, 0, 0, that means translate the object back to the origin, this doesn't appear to work. What we have to do in this case is store the transformation in some temporary variable, change the row for in that variable, and then assign the value stored in the variable back to the transformation. Now the row 4 was changed to 0, 0, 0 and the object went back to the origin. Copying the transformation matrix value from one scene node to the other would effectively match both the position, rotation, and scale of the two nodes, resulting in a full alignment. Let's create two teapots. Rotate the one teapot to an arbitrary angle and also scale it in local space along the X and Y. And let's scale the other teapot along the Z axis. Now we could try to write the short script where the source is going to be the teapot 01, the target, the teapot 02, and the target transformation matrix, the transform property, is going to be the source transformation matrix. Evaluating the script will copy the transformation matrix of the first teapot into the transformation property of the second teapot and effectively align the second teapot to the first teapot, also copying rotation, position, and scale. Obviously, we can copy only the position, which is easy. We can either use the position property or the row 4 of the transformation matrix, but we can also copy only the orientation, that means the rotation, and the scaling without changing the position. For example, in order to do that, we could copy the transformation matrix into a variable, set the row 4 of this transformation matrix to the row 4 of the target object. That means we take the position, rotation, and scale of this object, replace the position of this transformation matrix with this position, and then we write back the resulting transformation matrix into the target object. The result is the same orientation and the same scaling, but the position is preserved. We can also remove the scaling information from this transformation matrix and keep only the orientation. To do this, we could take the source scale from the transformation matrix scale path. If we would evaluate this in the listener, this is the transformation matrix and this is the scale path, which is the actual scaling along the X, Y, and Z in local space. And now we could take the row 1 of the transformation matrix and divide by the first component of the scale path, which is the scaling along the X. Then divide row 2, which is the Y-axis, by the scaling factor along the Y-axis, and do the same with the third row, which is the Z component of the source scale. Then we copy the position